Swayam Prabha. Digital India. Educated India.
Welcome to another lecture and introduction to machine learning. Today we will dive into the learning theory. So this lecture is going to be a bit more mathematical than the previous lectures. We will look at how different assumptions about classifiers lead to learnability, and we will first start by defining learnability. So the objectives of this topic are that we will define something called packed learning, probably approximately correct learning. We will derive packed learnability sample complexity. So basically how many samples are needed for some guaranteed learning outcomes such as probably approximately correct learning. And then we will get theoretical insights into model complexities, sample size and validation in terms of the complexity of the models. So before we get into what is packed learnability, there are some concepts that we should define. So let's first talk about what is error and what is training error. So these are two separate concepts in the sense that what we assume is that we have a domain set X. So this domain set X is basically from where the input samples are drawn. So this is your domain set, right? And we have a label set. So we have a label set which is basically the label for each sample that is drawn from the domain set. So this label set can be either, let's say, 0 1 for a binary classifier, or it can be -1 +1 depending on mathematical convenience. One of these two we will assume because there are certain equations or mathematical expressions that work better with 0 1. There are others that work better with -1 +1. The mapping from one to the other is quite trivial, as you can understand. So this is these are some of the basic definitions on which we will build upon to get towards packed learning. So out of these domain sets, not everything is given to us. What is given to us is a training sample S. So this is your training sample. And basically these are paired samples of samples drawn from X and Y. So basically what we'll have is we will have x1 comma y1 as a tuple, we'll have x2 comma y2 as a tuple, and let's say we will have xm comma ym as a tuple. Okay, so this is our training set. Okay, and basically what the learner will do, the learner will give us a hypothesis H. So this is a hypothesis, or also called a classifier, or we can also call it a predictor. What basically H is a function which maps the domain X to the label set Y. Okay, so basically if we take any xi, it will give us yi. So if we have h of xi, okay, what we will get is let's say an approximation of y, maybe not the actual y, so we will get yi hat. Okay, but we assume that the domain set and the label set, they are related to each other in the sense that we have we have a function f which is the true mapping from x to y. So this is a true mapping from x to y, and the samples that are given to us, the training samples that are given to us, they are such that yi is going to be f of xi. Okay, so as you can imagine, our goal is to bring yi and y hat I to be close to each other. Okay. So this is the correct function. Now what we also do is we define a distribution. Distribution is a distribution over x, probability distribution over x, because the domain set, for example, if you are looking at the set of images, they can be very random looking images which actually don't exist. There is actually a subset of all possible images that actually look like natural images, and then the label set could be -1 or 0 for cats and 1 for dogs, for example. So these are images of cats and dogs, which is a very small subset of all possible images. So that subset is defined by this distribution D, which is over x. So what we are going to say is that our error is actually over this unknown distribution, and this is unknown. So this is quite important to make note of that this distribution is unknown. Why it is important is because we can only approximate this distribution through the training sample S. So this is the unknown distribution over x. So what we are interested in minimizing is some loss over this distribution. So we want to minimize the loss over D and F, okay, for this particular distribution for an ideal mapping of input to output, okay, over the hypothesis H, okay. And what is that error? That is basically the probability of x being drawn from distribution D such that Hx is not equal to Fx. Okay, so this is the error that we are trying to minimize, alright. But what we can do, the only thing that we can do is minimize the training error, okay, because we don't know this distribution. So the training error is going to be this L over the training set S for that particular hypothesis, okay. And here what we will have is I belonging to all the training samples from 1 to m, okay, such that Hxi is not equal to yi. So if we count all of those and divide it by m, so basically it is our misclassification rate. So that is the training error, okay. So overall our error is going to be, let me write it in a clearer way here. So training error is the loss over S for a given hypothesis, right, and that is basically if we count all I that belong to 1 to m, okay, for which Hxi is not equal to yi, and we divide it by the total number of samples. So basically it is the misclassification rate. So this is what we can reduce, but what we are actually interested in reducing is the error over D, not over S. So what we what is empirical risk minimization is that when we say empirical risk, this is always defined over S, over the training data set S. Okay. So if we have a classifier, okay, if we have a classifier, let's say if we take argmin over H, okay, of the loss over H over S over of all H, then we will call it H of S. Okay. So this is the empirical risk minimizer. Minimizer hypothesis, minimizing hypothesis. So that means we have found a function that basically reduces the error over L of S, and if we are given any choice of function, so we assume that this Ls of H, if we minimize it over H, we will get this to be down to 0. When will we not get it down to 0 is when there is some restriction on H, when we are not able to choose any possible hypothesis, then we are going to have a problem. Okay. So these are basically, to revise again, you have true risk and we have and the empirical risk, but before we get there, is the question is basically driving down the empirical risk to 0, is that a good idea? The answer is that obviously it's not a good idea, because that can lead to overfitting, can lead to So what is a solution to avoid overfitting? The solution is to restrict restrict H. Solution to avoid overfitting is to restrict H to some class capital H. Okay. So we don't want to use any classifier, we want to use a classifier from a limited set, okay, from a limited class of classifiers, so that we don't overfit, and we will look at how why basically limiting the set of classifiers leads to better performance. Okay. So coming back to the true risk and empirical risk, so basically our empirical risk, right, is Ls of H for any hypothesis, whereas empirical risk minimization is achieved by Ls of Hs, where Hs is the one that minimizes the risk over the training set S, whereas our true risk is L df, okay, of H, that is our true risk. So what we do with this is that we have something called a realizability assumption to basically show that we can minimize, we can put some bounds on the true risk, okay, if we draw enough samples. But to do that, first we have to make certain assumptions. We'll slowly relax these assumptions. The first assumption that we have is that there is a realizability assumption. What that means is that first of all, let's see what is what we mean by realizability. So basically, let's say we have there exists some H star, some optimal hypothesis or a classifier, okay, that belongs to a class H, okay, and this is your hypothesis class. Okay, such that this LDF over H star is going to be 0, that there exists an ideal classifier within the hypothesis class such that we will have a perfect classification over the unknown distribution D and the unknown function f. Okay, it's a very strong assumption. So what is a hypothesis class? Let's basically take a look at that first. So let's say we have a one dimensional input x, alright, and we have a set of classifiers, okay, and the classification function is the following, that x is less than a, okay. So this is a threshold. So what that means is that I will choose a point A on this x axis, and I will label all the points to the left of it as 1, and I will label all the points to the right of it as 0. Okay, so this is our classifier. It's a threshold classifier. Now for each A, I can move the threshold around, and I will get a different classifier. Some of these classifiers will be good, some of these classifiers will not be so good. So if we have some training samples, for example, and they are labeled in a certain way, so let's say these are all labeled 1 1 1 and these are labeled 0 0, then I have a perfect classifier, at least for the training data. And if I move this threshold around so that I cross over any of these points, then it will be a less than perfect classifier, even for the training data. So I have a set of hypothesis or set of classifiers which is defined by this capital H, and within that I assume that there exists at least one perfect hypothesis or a classifier for which the loss is going to be, or the true risk is going to be 0. So it's a strong assumption, but we will relax it slowly, but for now let's go with this assumption. The other assumption that I have is, so before that let's define what is a bad hypothesis and a misleading sample. So the one assumption that I have is that my training set is IID training sample. What that means is that this training sample S, okay, it is drawn from the same distribution D and it is drawn m times, okay. So the joint probability of all the points in S is going to be a product of probabilities of the individual points in S. So this is an assumption that I have, that the input data that I get, the training data that I get, each sample is unrelated to each other, it's independent of each other, not unrelated, it's related through D, but otherwise it is independent of each other, and it is identically distributed. The probability distribution of x1 is same as that of x2 and so forth. So what is a bad hypothesis and what is a good hypothesis? So a good hypothesis, let's say we will give a definition of that, is such that if I take this loss over D and F, okay, and basically if I have a hypothesis H, okay, then this is going to give me an error or a loss that is less than epsilon, some threshold epsilon. Okay. So we have not defined this loss function. This could be a 0 1 loss function, for example, 1 for misclassification and 0 for correct classification. We will come to that in a bit, but for now it's a general loss function, and what we are saying is that if we take this hypothesis and over the entire distribution D and an underlying function f, if the error rate is less than epsilon, then this is a good hypothesis. If it is greater than or equal to epsilon, then let's say it is going to be a bad hypothesis. So this is a success. Okay, we are not being very strict that the error has to be 0. Okay. So the set of bad hypothesis set HB, okay, is going to be all the H that belong to capital H, okay, such that this loss over D and F of H, let us say, so here let us say equal to, is greater than epsilon. Okay. So this is our bad hypothesis set. In addition to that, let us also define a misleading sample. Okay. And we are going to connect the two. So a misleading sample M is basically all the possible training sets S that are taken from X, such that there exists H belonging to the bad hypothesis, the set of bad hypothesis, and but it gives very good performance on the training set. Okay. So what this means is that we can have samples on which if we do empirical risk minimization, on which if we have perfect classifiers such that the loss over S is 0 for that particular classifier, yet that particular hypothesis belongs to a set of bad hypotheses when we look at the overall distribution. That means it is not going to perform well in another resample from that same distribution D. Okay. So this could be a misleading sample, and that can happen probabilistically, it can happen. So what we are interested in is that how do we reduce the possibility of or the probability of having a mislabeled sample, okay, a misleading sample, by increasing the size of the samples. So if we have a large enough sample, then the probability that it is a misleading sample is going to be lower, and we want to basically explore that mathematical relation, and based on that we will show that there is a relationship between the error that is desired and or the accuracy that is desired and the sample size. So how we get there is that, let us say now we want to estimate the probability of this sample size. So basically the probability of M is going to be d to the power M, okay, because we are drawing M samples. This S that is drawn from X, LDF, okay, the hypothesis that was fit on S, it gives error that is greater than epsilon. Okay, so this is the probability of having a misleading sample. Now this is going to be less than or equal to, okay, sum of individual samples. Why? This is based on if we have P of A union B, okay, that is less than or equal to P of A plus P of B. Okay. So using this property, what we can say is that this is going to be less than if we take the sum of all hypotheses that belong to bad hypothesis, okay, d to the power M, S drawn from X, such that the empirical loss is 0. Okay. Now here this second term we can write this as a product because this was based on MIID samples. So this is going to be sum over H, so I will just say that this is again going to be less than or equal to the total number of hypotheses in H, okay, and then we are going to have a product of I is equal to 1 to M, okay, from the distribution D, we will draw xi such that h of xi is equal to f of xi. So it is misleading because it is doing very well, okay, but it is going to be a subset of that. That is why we have the less than equal to sign. Okay. So this is going to be again h, and this product will basically become 1 by 1 minus epsilon to the power m. Okay. Why 1 minus epsilon? Because the probability that we will get an error is epsilon, so the probability that we will not have an error is 1 minus epsilon. Okay. And then this is going to be less than equal to all the hypotheses that are in H and e to the power minus epsilon m. Okay. So notice that we are actually looking at the number of hypotheses, and because of that this bound on the error only works if we have finite hypothesis classes. Finite hypothesis classes. Which implies that the number of hypotheses in this class is less than infinity. Okay. So this basically gives us an idea of what is the relation between the error that we want and the sample size. So they are related through this function, and basically they are inversely proportional to each other, and they are related to the size of the hypothesis class through a log of the hypothesis class. So basically it tells us that if we want a smaller error, then we better draw a larger sample so that we reduce the probability of drawing a misleading sample. Okay. And if we have a larger set of hypothesis classes, if we have more number of hypotheses, more possibilities in the classifier, okay, and then we better have a larger sample to counter that. Otherwise, if we have a smaller set of hypotheses, then we need a smaller sample to guarantee that the performance will be less than epsilon. The error will be less than epsilon. So basically our sample complexity is such that for if we have a delta and an epsilon that belong to this 0-1 interval, okay, then if we have m, that m better be greater than log of h divided by delta upon epsilon. So this basically is our probably approximately correct sample complexity. So let us unpack this a little bit. What this says is that if you draw samples that are more than the log of the number of hypotheses in the hypothesis class divided by a constant delta, which is between 0 and 1, and so the log of the whole thing divided by epsilon, then we can ensure that the true risk is going to be less than epsilon with probability at least 1 minus delta. Okay. So this guarantees that true risk, what is true risk? True risk is LDF H with sample S, the empirical risk minimizer HS. True risk is going to be less than epsilon with probability at least 1 minus delta. Okay. So this brings us to probably approximately correct learnability definition. So let's say we have a hypothesis class H, okay. H is pack learnable, okay, if there exists two things. There exists a function m, okay, of this hypothesis class over epsilon and delta, okay, epsilon delta being between 0 and 1, okay, and it maps it to the set of natural numbers, basically number of samples, okay, and there exists a learning algorithm okay, such that if m is greater than equal to mh, okay, then with probability at least 1 minus delta, okay, this LDF of H, the hypothesis that is learned, is less than epsilon, okay. And a corollary of this is that every finite hypothesis class is pack learnable, which we showed in the previous slide, okay. So the finite hypothesis class could be a limiting assumption, but if you think about, for example, thresholds, these are not finite hypothesis classes. We can make any infinite hypothesis class into a finite class by using discretization. So discretization can lead to finite hypothesis classes. However, we would like to get rid of this finite hypothesis class assumption. We would also like to get rid of first the realizability assumption. Realizability assumption is quite limiting. If a hypothesis class is not realizable, in the sense that we cannot, there exists no hypothesis in that class that will ensure that true risk is 0. Forget about even actually having a learning algorithm to find that hypothesis, then we could be in trouble by having this assumption. So can we have some guarantees even if we relax this realizability assumption? Okay. So to remove the realizability assumption, what we will do is let's revisit the distribution D that we had. So we will change the definition of D now, and this D distribution is going to be over X and Y, in the sense that it's going to be a joint distribution. So this is a joint distribution over X and Y. Okay. And what we will say is that D small x is the marginal distribution of X. So at test time we are drawing from the marginal distribution dx, but at training time the capital S is drawn from the joint distribution, which is D over X and Y. Okay. So now we redefine the risk, the true risk, Now we don't have an f, okay, we have a joint distribution D, okay. So this is going to be the probability of xy being drawn from D such that h of x is not equal to y. Okay, so this is true risk. Okay. So this is going to be from the set D, okay, we are going to draw xy, okay, the probability that we will draw xy such that h of x is not equal to y. Okay. And we will define the training loss over S, okay, as before, and which will be this I belongs to the set from 1 to m such that hxi is not equal to yi. And divided by the total number of m. So this is the training loss or empirical risk. Okay. So what we say is that if we have a hypothesis class H, okay, all right, it is agnostic, pack learnable, okay, agnostic as in it doesn't assume that there is realizability, it is agnostic to realizability. It is agnostic pack learnable if there exists that same function mh, similar function mh, and a learning algorithm, okay, such that for all this epsilon and delta belonging to 0 1, and for all d over x and y, if we draw enough samples, okay, then with probability 1 minus delta, okay, LD, the risk of H is less than equal to minimum of H dash taken from H, LD H dash plus epsilon. Sorry, it should be LS. Okay. So there is sorry, LD, yeah. So there is some true minimum risk, okay. This true minimum risk need not be 0. If it is 0, all right, then it is going to satisfy the realizability assumption. But let us say if it is not 0, whatever is the minimum, right, on top of that we can add an epsilon tolerance, okay, and if we can draw a sample, right, from this such that the risk that we will get is going to be the true risk of that classifier is going to be minimum plus a tolerance of epsilon with probability 1 minus delta, then this hypothesis class is agnostic pack learnable. So that is the definition of pack learnability here. Now the question is, what is a learning algorithm? Okay, what kind of learning algorithms will give us this guarantee? Okay, is just fitting on the training data enough? Okay, that is basically what we are going to explore in the next few in the next few minutes. So we will need one more definition now, which is epsilon representative sample. What that means is that if we is there a sample size, if we draw from that an IID sample with that sample size, then we can assume that the error is going to be minimum error plus delta plus epsilon with probability 1 minus delta. So that is what we are going to go after. So what is epsilon representative error? So epsilon representative epsilon representative sample, let's call it S, okay, with respect to this domain Z, which is basically a combination of X and Y, the hypothesis class H, some loss small l and D, or capital L rather, and the distribution D, such that if for all H belonging to H, okay, the LS of H minus LD of H, okay, is less than equal to epsilon. If we can guarantee this, then it is an epsilon representative sample. Okay. So what is the probability of drawing a epsilon representative sample? Can we tie it to the sample size? If we limit that probability, if we say that that probability has to be lower bounded by 1 minus delta. So let us say we have an epsilon by 2 representative sample. So let us say we have an epsilon by 2 representative sample. Okay. So what is the how can we basically link it to the size of the sample? So what this means is that if we have an epsilon by 2 representative sample, then we can guarantee that the true risk of this sample of the empirical risk minimizer on this sample, okay, is going to be less than equal to minimum of H belonging to capital H, the true risk of any sample and any hypothesis, plus epsilon. Okay. So this is quite powerful, that if we draw from this particular sample, then we can guarantee this. So what we have is, where what is HS? It is the empirical risk minimizing hypothesis, ERM over the hypothesis class S for the particular training sample S, which is HS is argmin over H, okay, of LS of H. Alright. So now why would this guarantee it? This is because this LD of HS, right, is less than equal to LS of HS plus epsilon by 2, because it is epsilon by 2 representative, okay, and this is less than equal to LS of HS, LS of any H, not HS, plus epsilon by 2, okay, which is less than or equal to LD of any H plus epsilon by 2 and plus epsilon by 2. So where does the one of the epsilon by 2 definitely comes from here, the other one comes from any hypothesis class being epsilon by 2 representative. So that's how we get the epsilon by 2 plus epsilon by 2. So what this tells us is that if we have an epsilon representative sample, epsilon by 2 representative sample, then we can guarantee pack learning if such samples exist, okay, for a particular hypothesis class. So this gives us a framework for basically concentrating on reducing the training error for a sufficient sample size to guarantee that we will get a probably approximately correct learning. So now what we want to do is we want to show that the finite hypothesis classes are pack learnable. So for that what we will do is we will define something called uniform convergence, and we will say that a hypothesis class H has uniform convergence, okay, if there exists some function from that hypothesis class for uniform convergence sample size, alright, such that if the size of S, which is M, is greater than equal to mh uc of this epsilon and delta, then with probability 1 minus delta S is epsilon representative. Okay, so this is the definition of uniform convergence. Okay, so which means that if H has UC, uniform convergence, with sample complexity m h of UC, okay, then it is agnostically pack learnable. It is agnostically pack learnable with sample complexity mh. With sample complexity mh epsilon delta, that is less than equal to, now we have to tighten the bound, mh uc epsilon by 2 comma delta, okay, and empirical risk minimization over this hypothesis class is a successful pack learner. Or agnostic pack learner rather. And another implication of this is that finite hypothesis classes are agnostic pack learnable. Let us unpack this a bit. So the implication is that if you have a finite hypothesis class, such as for example, even if you have an infinite hypothesis class like a continuous threshold or a linear classifier that can take any value of slope and intercept, we can discretize it and make it finite hypothesis class. In this finite hypothesis class, if there exists, if we can draw samples that are epsilon by 2 representative, then basically we can guarantee that there is a sample size computation that we can do. If we draw more samples than that, then we will have the guarantee that with probability 1 minus epsilon that the error rate is going to be less than, 1 minus delta, the error rate is going to be less than epsilon. So this all depends on whether we have, whether our hypothesis class and data are cooperative enough. Okay, the hypothesis class is rich enough and the data is let's say in some sense smoothly labeled enough that there's some side that is labeled 1, the other side is labeled 0, such that the classifier works on that. If we can reduce the risk only on the data sample S, then we have some guarantees over the entire underlying data distribution D. Okay. So that's why we concentrate on only reducing the error on the training set, as long as we have enough samples. But this is not the to be taken as a panacea that every time we reduce the error on the training set, we will always get low error on the entire underlying unknown distribution D. That is because of the no free lunch theorem, which means that which says that for every learner, okay, there exists a task on which it fails. And it actually says that with certain probability. So think about it this way, that let's say we had an adversary creating training data sets for us, and that adversary has created the data set S such that we can fit perfectly on that data set using the learner, and but then it's drawn from an improbable sample of D, such that the classifier actually performs much worse on D. So that can always happen, and that basically is captured in the no free lunch theorem. So I will skip the details of no free lunch theorem. Those who are interested in this, they can refer to Understanding Machine Learning by Ben David and Shalev Schwartz. It's quite an interesting book to build the basic learning theory. It's quite explained quite well in there. Okay. So this leads us to the bias variance trade-off. So let's say we want to minimize the true risk over D using a hypothesis that minimizes the risk on the training sample. This is going to be going to be a sum of two different errors. One is going to be the approximation error, and the other is going to be the estimation error. Okay. So this is the approximation error, and this is going to be the estimation error. What are the definitions of these? So approximation error is basically how close can we get to an ideal hypothesis. So within this hypothesis class, okay, how much can we reduce the risk? Alright. So ideally we want this to be 0 for a particular hypothesis, but we limited the hypothesis class to some capital H. Why did we limit it? Because we wanted to prevent overfitting. So if we limit it, then we may not be able to go to 0. This is going to be greater than equal to 0. So how can we come closer and closer to 0? So if we can have, so this is going to be small for rich hypothesis classes. Okay, because you have more possibilities, you can come closer and closer to the actual H star that will make it 0. Okay. But when we do that, if we have small epsilon approximation, then we are going to reducing epsilon approximation can increase epsilon of estimation. And why is that? Because now we have a very rich classifier, and because the classifier is rich, your mod of H is going to be large. If mod of H is going to be large, then for a given training sample, the probability with which we can guarantee that the error is going to be less than epsilon, that probability will reduce. Or we will need a large sample size. So this happens because M depends on mod of H. Okay. So this is the bias variance trade-off that rich hypothesis classes can reduce approximation error, but they may have estimation error, large estimation error. So the next thing that we will show is that this because these finite hypothesis classes sometimes are not very useful, we are not going to discretize the thresholds or the slopes and intercepts of linear classifiers and so forth. Then in that case, how do we show that even if we have infinite hypothesis classes, they are pack learnable, okay, and they are actually pack learnable using empirical risk minimization, that by fitting the best classifier on the training data. Okay. So let's take the example of a threshold classifier. So let's say we have a threshold classifier, okay, and this is simply 1 if x is less than a, otherwise it is 0. Okay. Now we know that the sample complexity of such a classifier, what we want to do is that we want to show that the sample complexity of such a classifier is less than equal to log of 2 by delta, okay, divided by epsilon. This is what we want to show. So here A is a continuous threshold, and because it is a continuous threshold, it is an infinite hypothesis class. Yet we want to show that the complexity, the sample complexity of this class is limited if we want to guarantee some performance with a certain probability, okay, under the pack learning regime. Okay. So how we show that is that we will show the probability of drawing a bad sample is related to the number of samples. Okay. So let's first assume that let A star be the best hypothesis. This implies H star of x for this A star is going to be 0. One of x less than A star, okay, and this LD of H star is 0. Okay, let's assume this is the best hypothesis. Okay, and now let this is there be an interval A0 less than A star less than A1, okay, such that on both sides of this A star the probability of drawing a sample is epsilon. The probability that x is drawn from D marginal x, okay, x belonging to A0 to A star is equal to probability of x drawn from dx, x belonging to A star to A1, and both of these are epsilon. So we have this line and we have A star, and we are taking an interval where we have A0 here and A1 here, and we have epsilon mass here and an epsilon mass here. Okay. So you can see where we are going with this, that we are going to show that the probability that we end up with a bad hypothesis is related to the sample size if we fix this epsilon. Okay. This is again still based on the realizability assumption that that we are going to have a 0 risk when we have A star. Okay. So now let Bs for the training set S be the ERM threshold, ERM HS threshold, which means that this is going to give us the best performance on the training set. It is going to give us zero loss on the training set. Okay, so let's say we have a B0 that is less than greater than equal to A0, and B1 which is greater than equal to A1. So this is going to be less than equal to A0. Okay, sorry, this is greater and this is less. This will imply that LD of HS is less than equal to epsilon. Okay, if we have the, if we sample from this these two intervals, then we are going to have the true risk that is going to be less than epsilon. Okay, so the probability that the sample is drawn from D to the power m, okay, such that B0 is less than A0, okay, is same as the probability that S is drawn from dm, okay, for all xy belonging to S, such that x belongs to A0 comma A star. Okay, and this is equal to 1 minus epsilon, all right, to the power m. Okay, and this is going to be less than equal to e to the power minus epsilon m. Okay, so what you can see is that when, if I apply the same logic to B1, what I will get is m is greater than equal to log of 2 by delta, okay, divided by epsilon. Okay, so which implies that this probability is going to be less than delta by 2. So we can see that we can actually have a sample complexity that gives us some performance guarantee even when the finite when the hypothesis class is not finite, and this also applies to other infinite hypothesis classes so long as they are simple. Now that notion of simplicity for infinite hypothesis classes is something that has not been defined. The notion of simplicity for finite hypothesis classes is as simple as the number of samples or the number of hypotheses in that class, but now because the number of hypotheses are infinite, we need an alternative definition of what is the notion of complexity or simplicity of a hypothesis class. So here, so to define basically the complexity of infinite hypothesis classes, we use something called VC dimension, Vapnik-Chekosnovic dimension, behind the people who proposed this. And basically what we are saying is that for a particular classifier, okay, if there exists a set of points C, okay, such that the number of set of points is equal to D. What is C? C is C belongs to C is a subset of X, just X, subset of the domain X, okay, and it is D that can be shattered. I will come to what it means to be shattered, can be shattered, okay, by H. And there exists no C such that if C is the size is greater than 1, or for all C where the size is greater is increased by D, then it is not shatterable, it cannot be shattered. Then VC dimension of H is equal to D. Okay. So let us unpack this a bit. So first we need to talk about what it means to shatter something. So let us say we have a particular set of points, right. So let us say we have these 3 points and I can label them any which way as positive or negative samples. So how many possibilities I have? I have 8 possibilities. The possibilities are that these are all minus minus minus, or this is minus plus minus, or minus plus, so basically 2 to the power 3 possibilities I have. Okay. Now imagine if I have a set of oriented hyperplanes. A linear classifier, a set of oriented hyperplanes. On one side of it is the positive sign, the other side of it is the negative sign. So let us say if these were all negative signed, then I can basically I can correctly classify this using this particular classifier. On the other hand, if I had one of these as positive signs, I can perhaps move this and still classify it correctly. On the other hand, if I had 2 positive ones, then I could have moved it and still classified it correctly. In case I had all positives, then I could have still classified them correctly. So if the set of hypothesis classes that I have is a line in 2 dimensions and the number of points that I have are 3, right. So then I can shatter them in the sense that I can have any arbitrary positive and negative labeling of these points using the hypothesis class of line. I can correctly classify them. So that means a line shatters 3 points in 2 dimensions. The set of lines, the set of linear classifiers shatter 3 points in 2D. Okay. So now let us come back to VC dimension. So if the set of classifiers, the infinite hypothesis class that I have is a linear classifier and X is drawn from 2-dimensional domain. X is a 2-dimensional domain, it is a set of points in a 2D plane. Then if I have at least one configuration of points, a non-pathological configuration of points, C belonging to this distribution is a subset of this domain X, such that if the size of C is D, so in this case 3 points, D is 3, and it can be shattered by H, it can be shattered by linear hyperplanes. Okay. But if I increase the number of points, then there is no configuration of 4 points that can be shattered by lines, then the VC dimension is going to be 3 of the linear hyperplane. So is it true? So think about it, if you have 4 points, then you cannot have any 4 points in any arbitrary locations such that all 16 sign assignments or label assignments can be classified by the linear classifier. So the VC dimension is going to be 3. Let's take another example. So let's take the example of a threshold classifier. So let's say we have a line, one dimension, and basically our classifier is that x less than a is our classifier. Okay. So only the left side of a is going to be positive, the right side of a is going to be negative. So let's say this is our training sample, and this can have, its label can be either 1 or 0. Okay. So here I can have, if it is 1, then I can have a here. If it is 0, then I can have a here. Okay. So this is 1, this is 0. So that means VC dimension of this classifier is at least greater than equal to 1. Now let's take 2 points. So now the number of labels I have are 4. Okay. So I can shatter this by putting a here. I cannot shatter this. I can shatter this by putting a here, and I can shatter this by putting a here. But this particular sample, this particular labeling, I cannot shatter. So VC dimension is less than 2. So if it is greater than equal to 1 and less than 2, then the VC dimension must be 1. Okay. So here VCD is VC dimension of this particular classifier is equal to 1. Let's take another example of when the VC dimension can be 2. Okay. So here we will take an interval. So let's say again we have 2 particular points, right, and our classifier is that x only belonging to a comma b. So we have now 2 parameters to the interval a comma b is going to be 1. So again we have, let's say we have 2 samples and we have 4 possibilities. So this is 0 0, this is 0 1, this is 1 0, and this is 1 1. Okay. And we want to now choose an interval. So this interval of a and b can be the following. Here the interval can be this interval, here the interval can be this interval, here the interval can be this interval, and here the interval can be this interval. So basically we can, now the VCD is at least greater than equal to 2. Now if we go to 3, then we can easily construct a case, right, where let's say we have 0 in the middle and 1 here and 1 here, that we will not be able to shatter this. So VC dimension is less than 3 and VC dimension is going to be 2 in this particular case. Okay. Let's take an example of a rectangle in 2 dimensions, axis aligned rectangle. Okay. So here let's say we have not just x but we have x1 and x2, and basically let's say our classifier is axis aligned rectangle such that inside the rectangle is 1. So if we have x1 belonging to AB and x2 belonging to CD, okay. So basically it's a rectangle like this, inside is 1, outside is 0. Okay. So now if I take any 4 points and I choose any labeling of 0 1s, okay, so I can I can enclose one rectangle, I can enclose sorry, one point, okay, I can enclose 2 points, any 2 points including diagonal points, I can enclose 3 points, and I can enclose 4 points. So basically any labeling can be shattered, so VC dimension is going to be greater than equal to 4. Now on the other hand, if I have 5 samples, then and the middle one is 0 and the other 4 are 1s, then I cannot shatter it using an axis aligned rectangle. So the VC dimension in this case is going to be 4. Alright. So now you get an idea of 3 or 4 different infinite hypothesis class classes whose VC dimension is finite, and how to calculate the VC dimension, which is not always easy, but we know how to calculate it now. Let us take the VC dimension of, let us see an example of a VC dimension that is infinite, and see how it is actually not related to parameters. Before this it seemed like when we had one parameter, which is just the threshold, VC dimension was 1, when we had 2 parameters the VC dimension was 2, etc. So which is not always the case. Okay. VC dimension is not always the same thing as the number of parameters, or even related to the number of parameters. It is related to the number of parameters if the functions are of a certain type. For other types of functions it may not be related to the number of parameters. Let us say take the example of basically sine of sine AX. Okay. So when the sign is above, when the sign is positive, then we will have a positive class. When the sign is negative, we will have a negative class. Instead of 0 1, now we are looking at -1 +1 labeling. So in this particular case, we can actually have infinitely many samples, and we can give them arbitrary -1 +1 labeling, yet we can construct a sine wave, okay, by carefully choosing the scaling parameter such that it basically puts them in either the trough or the valley, in any which way we want. So we could even have, for example, something that like puts these two out and these two in, and something like that. So by slightly changing A, we can have a very large change in how the sine wave behaves away from the origin, for example. Okay. So in this case, the VC dimension is going to be infinite, although we have only one parameter. So it's not always related to the number of parameters. They can be like such pathological hypothesis classes with very large VC dimension. So as you can imagine that they don't respect sort of like the continuity of the input space, and when they don't respect the continuity of the input space, then they can do arbitrary labeling, but that arbitrary labeling usually it may not generalize very well, because we are trying to go towards the idea that we need to control the VC dimension. Okay. So basically there is a theorem now that says that if the VC dimension is not finite, then the hypothesis class is not learnable. Okay. So an example of that is, let's say if you have m different points, okay, and these m points basically form the training set S, and if we have infinite VC dimension, m can be arbitrarily large, and we will be able to shatter them using the hypothesis class, one hypothesis from that hypothesis class. But then we can choose another m set of points that have completely opposite labels, and that will completely nullify the learning that we have. So if we can explain everything, then we basically have explained nothing. So infinite VC dimension hypothesis classes are not learnable. So this brings us to the fundamental theorem of packed learning. The fundamental theorem of packed learning has 6 different equivalent statements. Okay. So the statements are the following, and some of these we have already seen, that if we have H that has uniform convergence, it is equivalent to having empirical risk minimization, being a successful learner, successful agnostic packed learner for H. It is equivalent to having H being is an agnostic packed learnable class. It is equivalent to having H is packed learnable. It is equivalent to ERM, empirical risk minimization, is successful packed learner. For H, and it is equivalent to saying that H has finite VC dimension. Okay, so the proof is something that I will not cover in this lecture. The proof is very well illustrated in the book that is mentioned at the bottom of this slide. But the building up of the proof is what this whole lecture has been about. So basically, what this means is that it gives us a couple of takeaways before we end the lecture. That if you have to choose classifiers, okay, choose classifiers whose VC dimension is finite, okay, and the sample complexity has to be scaled with VC dimension, with model complexity, which means that if you are going to use a classifier with larger VC dimension, then we should have training samples that are larger, because otherwise we risk overfitting. We cannot guarantee that the delta is going to be large, that we cannot guarantee with enough 1 minus delta probability that the training sample is representative of the underlying distribution in terms of performance of this particular classifier. And then basically it leads to, if we truly want to get an estimate of how the classifier will perform on test data, then we have to get an estimate of the error and its variance, okay, using rigorous validation or cross validation. So when we do that, then in some sense we also minimize the risk of not using enough sample size, because here the assumption is that your test data set or your validation data set is actually a representative of the true underlying distribution. So by testing the performance again and again on that, if we get a sense for not just the error but the variance in error by drawing multiple subsamples, bootstrap samples or subsamples from that particular distribution, we can guarantee that we are not overfitting and we are reducing the bias in the classifier. So this builds up the entire theory of why we need validation, why we need regularization. Regularization reduces the hypothesis class, and it guarantees performance based on whatever we have seen on the training data set and so forth. So I hope it gives you insight into the earlier part of the course of why we were insisting on some of these things. Thank you.